Hello, I'm Nikola. I'm a physicist, but I also spent the last 15 years not just doing physics, but also looking at how we can use different computational tools to and take computational tools like as a broad category to help us both in the ways we do research and in the ways we do education. And I'm coming here to share with you some ideas and some examples and to try to steer discussion in that direction. Before we start, like by way of introduction, I'm coming from Belgrade, Serbia, where I did my undergraduate degree in physics, and then I moved to England, in the group of Stuart Adams, to do PhD in aerophysics. After that, I moved for one postdoc in Aarhus and another postdoc to Paris. And during this time, we were not just publishing papers, but we were also creating like a number of different tools, both web services and open source libraries. And particularly I would like to highlight two interactive books. One is Read Book Physics, which was first actually Institute of Physics publishing book that was using all the potential that EPUB 3 format has to offer for the interactivity in the publications. And more recently we released an interactive guide to quantum optics, which is a collection of basically visualizations and ideas from quantum optics that can aid your teaching of the subject of quantum optics, but also the quantum physics in general. That does not only do that, but also unites many of the examples and web services and visualizations that we created in the previous time. Now, more recently, the last 4 years, I'm working actually in quantum industry with Quantum Machines, which is one of the world leading manufacturers of the control electronics for the upcoming quantum computers. We work with both leading research labs and universities and also industrial labs. And more precisely, like last 2 years, I'm in charge of the compute infrastructure for the new and upcoming quantum data centers. So the first instance of which is physically on the premises of Tel Aviv University, so it's like IQCC, and that computer is there, but it's actually accessible for the people all around the world, and they can run experiments there. And I think it's important also examples how you can run with on the parse level with open architecture to provide basic access for both research and education to very expensive resources on a global scale. So our objective today is education, but education has many facets, and I want to focus on particular things that I find very important. So education for me is something that empowers us to engage with and shape the world. And by world I mean the society, technology, but also the value system, because the values are ultimately what makes us do things. By expanding that, so by expanding our capacity to see, question, and test, by making experiments, prototypes, and so on. And importantly, by embedding us in our local, context and moment, because without that context and moment, like we don't actually have really agency really to make and see, the things that are important for our local societies. And in this beautiful 17th century Ming Dynasty scroll, you can see, you have these mountains and clouds and forests, and somewhere there by the river, you have scholar reading and contemplating, the world. And this is basically the audience we need to serve. I think it's important that we keep this idealistic image in our minds before we start imposing different educational structures. More succinctly, Emily Dickinson said that he has the facts, but not the phosphorescence of thought. Phosphorescence of thought, very beautifully said. And I think for our students, it's important not just to provide them the facts, and correct answers, but actually to provide them, agency, capability to see, to be critical, and to understand what are the possibilities and what choices should be made, in the local context of the local communities and societies to make, changes. So how I'm planning to entertain you for the next few minutes is I will focus on three topics. The first one is being how we can move from mystification to explanations in quantum physics. Then how we can move from teaching paths to teaching design spaces. And finally, how we can move from teaching abstractions to teaching actually experiments. Now, all of this under real-world constraints. So first, the real-world constraints is inner. It's our brain. Our brains are lazy, and they need, first of all, some combination of playfulness. So we're going to tap into this childish, potential for creativity that makes us move around and discover things. And at the same time, we need something to provide a focus for our thinking, for basically our theorizing, so that we don't get lost while we move in this large space of the world. Now, there are also external constraints, and we have limited amount of time, we have a limited amount of money, and sometimes we're not born in the backyard of some very rich university. So we'll see how we can tackle basically the three above topics under these constraints. So to start with, I think that a lot of reasons why quantum is still like somewhat mystified field compared to, let's say, electromagnetism is that we don't actually use correct visualizations, fully correct visualizations for the topics we discuss in quantum. So I can give you one example. So we all use Bloch sphere to describe like singular qubits. And we know that when we do 2 pi pulse on the Bloch sphere, we end up at the same point. Now, except when you compare that singular qubit with another qubit, this single qubit now has a minus sign assigned to it. And this is because a Bloch sphere is actually incomplete representation even on a single, spin 1/2 system. For the spin 1/2 system, if you cannot neglect, relative phase with the rest of the world. And of course, it does not work with multipartite, multi-level systems. So it has its very many limitations there. On the other side, we can draw level diagrams, and they work with multi-level, multipartite systems, but they really don't represent any coherent dynamics there. It's very little, that element is completely being lost. Now imagine if we can actually combine the two and provide full representations. And that's what we did here, where with these two basic blobs that are corresponding basic to energy levels, but now you see in the dynamics, you not only see that you get the minus sign, you also see actually the phase of the driving and many other things. So this picture is actually calculated based on the full Hamiltonian and the state of the system. So both driving and the state of the energy levels. And actually, it's one-on-one mapping that works also for the multi-level and multipartite systems. So why is this important? Well, because we should think about these things, not just this impetus to build new and accurate representations, not just as new visualizations, but also as a way to provide tools for thinking and to focus. Important focus, while we move around, different spaces, exploring different papers and so on. And having accurate representations that are not hiding anything, and that actually when you understand how they're made, you can in your head integrate physical dynamics is very important when you try to create new protocols and try to create come up with new ideas. Another way how mystification creeps into the quantum is often is often through very dense papers for which we don't have enough time to go into depth and to read them fully, and there is always something like that. Now what we can do then is, instead of just writing the papers, we can actually create object-oriented libraries that are going to expose basically information to different abstraction levels to the users that don't need basically then to go and understand every single part of calculations, but can actually formally use this as a building block for bigger calculations. So that's what we did with ARC for atomic physics. So we combined both theoretical method in atomic physics with data about atoms, and we created basically a library that is now used not only by master students. Now master students can create, for example, in a limited amount of time, research works that are actually interesting also for cutting edge research, but also it's used by the researchers in neutral atom quantum computers, with Rydberg atoms, and also for atom sensing with Rydberg atoms. So it really, this type of very well designed library actually spans the full spectrum from education to the cutting edge research. Now creating such abstraction levels might seem simple. And it's not simple. You can easily, create a floor with a hole in it, and then you understand, well, actually, this is not a good abstraction level because I then actually need to go into that hole and, understand what's going on below. But, creating abstraction levels with object-oriented programming is basically something we, as a physicist, have been doing ever since we wrote first equation. And this is just natural continuation of that story that is more scalable for more complex examples. Importantly, with ARC, we also actually expose this at the end of the day also as a web service again, 10 years ago, and you can find it, on Google also if you don't want to install anything, you just want to get, some numbers to help, your quick back on the envelope calculation. Okay. Now, so far I've been telling you one story, and this is how we teach. We tell stories. We teach. We take students and we show them certain path and tell them, explain them what happens along this path. But what is important, especially in quantum space where we're still developing a lot of things, is also the students see what is beyond the path, what is on the edges of the path, what can be changed. And this is the design space. So one way how we can teach design spaces in a limited amount of time is by providing interactive figures, like the one shown here. So what we see here has two important elements. One thing is that we see that we have two basic visualizations of the same thing, which allows us on the one side to combine like two different viewpoints, and also to think about alternative visualizations, alternative viewpoints of the same subject. And at the same time, we can move in not one-dimensional space, but actually in this case in three-dimensional space. So some paths in this three-dimensional space are so famous that they actually have protocol names associated with them. But then when you stride along, adjacent paths, then you see that, how the theory breaks down, what are like, different edge cases, and it's surprising even for experts in the field sometimes. And this is, this surprise is actually where, you have this element of playfulness, because this is really what pushes you then, to explore and to try to understand all of these different cases. And maybe somewhere there are the new protocols hiding. Now, another place where we need to teach design space is experiment apparatus design. And this is the way how we extract information from the physical world. And ultimately, it's multidisciplinary thing where you try to combine both mechanical engineering and electrical properties and mechanical properties, and combine everything in 3D space and optical properties. You often misuse also some third-party technology, but not in a way it is written in the manual, but you basically hack the physical space to create something new, some new apparatus. And this is a skill that is taught usually at the PhD level, but it's actually very important. It's usually taught by, if here, for example, we have like a old Titan Sapphire laser from ENS lab in Paris. And if you're there, you can go to somebody who has been a long time in the lab and can explain you about these things. But not everybody lives, in the backyards of the, like a rich institution. And also, I think it's some skill that actually more generally people can acquire if they're exposed to the people who continuously hack the the technology to create new experimental apparatus. So how we can do this at scale? So we can take basically, because everybody knows this all the research apparatus that collects dust somewhere on the shelves. We can actually take multiple photographs of such apparatus and create 3D models, so that everybody now online can find and see how these things look like. And then we can go one step further and actually make annotated models, so that you attach actually text, you can attach additional visualizations and diagrams, you can have like audio description, you can have a point and tell type of description, add equations, and this type of analysis of experimental setups is important not only for if you want to prepare students for the new experimental lab, but also even if the students don't have physical experiment actually at their universities, they can still think about what are the reasons that for this particular layout, what are the critical considerations that went into designing such an apparatus. And I think this is where these experimental skills are being actually passed. So that's the way how we can teach cross-disciplinary technological basic misuse in 3D, which is what fundamentally experimental setups are. Finally, when you teach a new field or you give a seminar, usually you have at the bottom of your lecture notes some list of references. They usually look like this. Now, can we do something better, something more engaging there? What we can do, we can map these references in the space, with x-axis being actually time. And now the links are like citation context for different references. So for example, if you click on a particular reference, you can see how it's been referred into future papers, and that often tells you more about the paper than actually abstract of that paper. You can find, basically click and find, exactly where and how the things are being cited, and then you can start actually taking this literature and projecting it on the axis of your interest. So you can first filter, the papers that are maybe cited in multiple papers or multiple times. Then you can filter papers that only mention certain topic in the citation context, and by doing so, you're basically projecting this multidimensional space of the literature into axis of your own interest. So, and it's even for experts in the field, you always discover like some new interesting edge cases, and this is where actually real science happens, when you start connecting the corners, and you see the ideas as rivers in space, in a time space. So literature at the end of the day is also data to be manipulated, projected on axis of interest, and shared. And this is important through the web service like this. You can annotate the literature corpus and then share it with your people, with your students and your colleagues to further explore them. Finally, how we teach quantum, it can be like very abstract. You can teach gate as a matrix multiplication, where you multiply, bang, you have a new state. Of course, in reality, it does not happen like that. Usually, you have some continuous, coherent quantum evolution that takes time to happen. Now, in order to go into the experiments for this, you need to go into the basically like low-level, pulse-level world where the Hamiltonian actually evolves continuously in time. And running experiments like that used to be very expensive. Now, what we've done in the IQCC that I mentioned at the beginning, this Quantum Computing Center, is it basically allows students to write very detailed descriptions what they want to do as a code, and then this code, they submit this thing, and this gets executed not only on the control electronics that controls directly the qubits, but they can also like run something on the different test measurement equipment, and even on the classical server they can run like some very fast feedback loops within the coherence time of the system. And all of that takes time for like few seconds. So one student runs for a few seconds, and then the next student, everything is reconfigured for the next student that runs again for a few seconds. So this time shared, and they get, of course, at the end, real data. In this case, like a simple T1 measurement. So this time shared access to expensive resources, I think, is really a blueprint how many national hubs and even on the whole continent, we can establish, centers that will allow us to share these expensive resources and use publicly funded initiatives to actually give access to these very expensive resources to a large number of people, large number of students, regardless of where they are actually. What's also interesting about these things is that here the design space is so large, you can control and change so many parameters that actually people are doing research on these systems. And tasks are equally, if you want to set up end goals to our students, the tasks can be not completely defined so that you can actually at the end of the day score only continuously output without actually looking at how the things are implemented, because there's so many ways, for example, to implement 2-qubit gate. And you can, for example, continuously score on the fidelity of the gate, but you don't need to go and to enforce that students need to do in particular way. Then again, they can also explore this design space there. So we already demonstrated this, with, for example, having like 50 students from America region accessing at the same time this computer, and then from Asia Pacific region, and then from Europe region. So it's something, although the computer physically sits on the premises, in this case in Tel Aviv, it's actually something that is globally shareable. So I want to conclude finally with question is how we imagine education. I think it's a very important question, and sometimes in discussions of education I have this picture of linear path, and there's some obstacles and we need to jump over certain hoops. And if you're good at this, here in the crowd you have your family cheering, but also your future employers. And I think this is not very healthy picture of education, and it's not something we should be striving for. I think it's much better if we imagine education as creating a Japanese garden, or teaching really as gardening. So Japanese gardens might look like something that is natural, but it's not natural. It's designed by somebody to enhance certain ideas and certain things in you while you move through this space. You can move, with the teacher across certain path, but to see also what's on the edges of this garden, on the edges of these paths. And you can also explore alternative paths there. So I hope that I persuaded you that there is plenty of room in the computational world for creating digital knowledge gardens and educational spaces, and really connecting them with the whole world. Now with this, I would like to thank my co-author Stuart Adams from Durham University, and also my collaborators from the IQCC team in Quantum Machines. And if you have any questions, I can take them either now, or you can also check my website, where you will find also more specifically like many of the resources that we created that I showcased here without naming them each. Thank you very much.